Hi, today I want to give you a quick overview of our unit on heat and temperature. One of the first things we discussed were the different temperature scales, and so there's the Fahrenheit scale, which is on the empirical system, which is mostly the United States or the US uses the empirical system. Then there's the Celsius scale, which is on the metric system. Or another way for saying metric system would be the SI system. SI stands for System International. The third temperature scale that we should know is the Kelvin scale, and so that's the scientific scale, so we would use that in science. You should be familiar with how the Kelvin scale and the Celsius scale compare. 0 degrees Celsius is the same as 273 Kelvin. So if it was 10 degrees Celsius, we should be able to convert that to Kelvin. That would be 273 plus 10, so 283 Kelvin. If it was 20 degrees Celsius, we'd have to add 20 to 273. So that would be 293 Kelvin. Next, we should be familiar with how to calibrate a thermometer. To calibrate a thermometer, we need two temperatures we're certain about. So we take a glass tube, we stick it into something like the melting point of water, which is 0. We wait for the liquid to contract, for the particles to slow down, and then we make a mark on our glass tube that says 0. Then we stick it in another temperature that we're certain about already, and that might be the boiling point of water. We watch the particles in the red liquid, they'll move faster and faster and they'll expand, and we make a mark. And now we take a ruler between 0 and 0 here and 100, and we make equal numbers with our ruler, and now it's calibrated. We should be familiar with different types of thermometers. So this is the thermocouple. Thermocouples are located in devices that have temperatures that are really high. So a thermocouple might be found in an oven or a huge furnace. So it records high temperatures. It converts electricity into a temperature reading. This lady has a clinical thermometer on her head. It has a very narrow temperature range. It might start at 35 and go to maybe 41, because its job is simply just to measure body temperature. Healthy normal body temperature is about 37 degrees Celsius. So it's green here. That means she's within healthy range. So that's a clinical thermometer. Here are some other examples of types of thermometers. So this is called a bimetallic strip. And when we heat a bimetallic strip, it bends or curves away. So bi means 2 in metallic metals, so it contains 2 metals. Notice it always curves away from the certain metal. So usually a metal that expands fast, like copper, Cu, and a metal that doesn't expand as much, maybe something like tin. And so the reason it curves like that is the copper, its particles are moving faster and faster and faster at a greater rate than the tin, and so the copper starts to stretch out and expand, causing this curve to happen. Another type of thermometer we should be familiar with is the thermostat. And so if we look inside a thermostat, we should know how it works. Here's a bimetallic strip coiled up. There's a glass tubule with a bead of mercury. So in this picture that I'm circling, what's happening is the mercury, which is a metal, is connected to these electrical contacts down here in green. and electricity is flowing through a loop down to our furnace in the basement usually, and it's telling the furnace to turn on. So the furnace is in the basement, furnace. But as the furnace is on, the room starts to heat up, and eventually the coil here starts to expand, and it changes its angle of inclination. It tilts, and that causes the glass tubule to tilt down, and the bead of mercury slides away from the electrical contacts, and now there's no connection. There's a gap in the electricity. Here's a closer look at it. See the gap here? And so we've just flipped it around, but the mercury is over to this side now, and if there's air here, the electricity can't flow through the loop to the furnace, and it shuts off. We should be familiar with the particle theory and how that works. All matter is made of tiny particles that we can't see. They're invisible. All particles in one substance are the same, but if we look at a different substance, those particles are going to be different. We should be familiar with the attractive forces between substances. Solids versus liquids versus gases have different attractive forces. Solids have the strongest attractive forces because they're closest together, so they have the highest attractive forces. Gases have the lowest attractive forces, and liquids somewhere in between. We should know that particles are always moving, and the more heat energy they have, the faster they move. And we should know that particles have spaces. Solid particles have the least amount of space, then liquids, then gases. Here's states of matter. Notice how they arrange in different containers. This is just showing you how hot water particles will move a lot faster than cold ones. We should know our different changes of state. So melting, evaporation. Let's talk about sublimation. Sublimation means that it basically either a solid is heated with so much energy that it jumps to a gas, like dry ice. If we put dry ice into a room, it'll turn from solid carbon dioxide into a gas, a fog. Or sublimation down is a gas that's cooled really quickly down to a solid. For example, frost on our windshields might be sublimation down. During the day, there's all the water vapor in wintertime. You go to bed at night and you wake up in the morning and all that water vapor has been converted to solid frost on your windshield. That might be sublimation down. We should be familiar with a heating curve. Substances can go through phase changes, and these plateaus on the heating curve indicate it's gone through a phase change. So here's a plateau and here's a plateau. So there's a phase change here and there's a big phase change here. We should recognize the uniqueness of water. Most substances, when we cool them, they contract. The particles get closer together and they take up less space as a result. However, water has this unique feature where, let's say water is at 7 degrees Celsius. Look at all the space between the particles. However, when we cool it to -4, there's actually more space now in this picture. So it expanded. So water is unique in that it's one of the few substances that can expand or take up more space when we cool them. Because most substances, when we heat them, the particles move faster and they take up more space, and when we cool them, the particles move slower and they contract and take up less space, we have to plan for this when we're building things. Railroad ties have gaps to allow for expansion. Bridge decks have these gaps right here to allow for expansion and contraction. We should be familiar with conduction, which occurs best in solids, and in fact metals, because they're high in density, metals have particles that are really close together. And then if we even just look at all the metals, something like gold is really dense and it would contract well. Copper, Cu, is also a high density metal. And so notice this animation is showing you that once we heat one particle, it collides with the other, passing on heat energy. That's how conduction works. We did the butter test, and what we found out in this lab was that copper was the best conductor of heat. We should know how convection currents work. So as we heat a liquid or gas, because convection currents only work well in liquids or gases, the particles in this area above the flame start to move faster, they spread out, they take up less space, and they get lighter, and they float away. As they get away from the heat, they start to slow down their motion, they get closer together, and they get heavier and they sink. And then what happens here, we create low pressure. When we move particles away from an area, there's a low pressure system. Over here, by comparison, the air particles are in high pressure. Naturally, they get sucked back into the loop because particles like to go from high pressure to low, and that keeps the cycle going. We should know how radiation works. There are different types of radiation. Gamma rays are the strongest, then X-rays, then UV rays, then infrared, then different types of radio waves. And the difference between something really strong, like a gamma ray, and something really weak, like a radio wave, is the wavelength. So if we draw a wave here, here's my wave. The distance between the two tops of the bumps is the wavelength. Gamma rays would have a really tiny, short wavelength between the bumps, whereas radio waves would have large distances between the two humps in a wave. We did this lab and we found out that black objects that are dull, so dark, dull objects, absorb radiant energy well, and white, shiny objects reflect radiation well. We should know that properties of radiation, so they come in different types, which I explained. They move very fast, 300 meters per second, and they're absorbed and reflected depending on whether they're dull, dark, absorbs, shiny, whitish, reflects. We should know the two different types of heating systems. This forced air heating is much better, and what happens is you heat air in a furnace, and then it's sent out vents in the room, and then uses convection currents. So actually it goes this way, sorry. The cold air is sucked back in right here, back down to the furnace, and then the hot air is pumped here. This is an older style of heating. It's called hot water heating. And so what happens is the water's heated in a boiler in the basement, and then the warmish water, which is light green, is sent through a radiator. Then the radiator heats the air in the room. This is way less efficient because it takes a lot to heat water. We should know the two different types of solar heating. There's active solar heating, which has these panels on the roof, and underneath is a liquid like water or antifreeze, and the liquid heats up thanks to the help of the solar collectors, and then the liquid's sent to the basement. In the basement it's stored and then pumped through pipes in the floor, and then the pipes heat the air in the room through convection currents. In passive solar heating, all you have are windows, and the windows should be strategically placed to get the maximum amount of sun. So the sun in the northern hemisphere comes from the south, and if you're below the equator, so you're in the southern hemisphere, the sun comes out of the north. So you want to make your windows face that way. We should be familiar with thermal conductivity. The higher the thermal conductivity, the better it is at conducting, and the poorer it is at insulating. And we should be familiar with R values, sometimes called RSI. The higher the R value, like right here, the better it is at insulating or resisting heat transfer.